Hello, my name is Shervin Naeli, and today we're going to be going over basic orbital mechanics. To fully understand this video, I recommend that you are currently taking or have in the past taken an AP Physics 1 or an equivalent college level course. Sections of this video will also involve calculus. Ooh, scary. If you aren't familiar with calculus on even an introductory level, I'd maybe recommend skipping those segments. If you need a crash course in the matter, I would recommend you watch 3 Blue 1 Brown's Essence of Calculus playlist. Next slide, please. Oh god. Here's an outline of the video. We're going to start with Kepler's laws, then move on to Newton's law of universal gravitation, segue into centripetal force, then stop by a derivation of Kepler's second law before we go back and derive Kepler's third. Finally, I'll finish off with escape velocity and the V-Viva equation. How exciting. Okay, so Kepler's first law, the orbit of every planet is an ellipse with the sun at one of the two foci, or if we were to generalize this outside of our solar system, the orbit of one body around another is an ellipse with the body being orbited at one of the two foci. What is the foci of an ellipse? Well, let's get into it. Okay, so let's quickly review the ellipse. In previous math classes, you may have seen a setup kind of like this one, where you say you have a rubber band, you have two notches or pins, and you use the rubber band, you put a pencil in the rubber band, and you kind of trace out a circular thing. Well, the essence of the ellipse is just that. It's the idea that if we were to take any point on the ellipse, right, and we were to calculate the distance between the two foci and that point, so let's say D1 and D2, these are the two foci, that D1 and D2 are equal to a constant. So that if we were to take a different point, the same D1 plus D2 would be the same, right? And you can think about how that corresponds with our previous perception of the rubber band and, or I think it's a string usually because a rubber band would flex, but a string and the two thumbtacks, right? And if you want to look into this more out of your own curiosity, again, 3 Blue 1 Brown, brilliant YouTube channel. He has a fantastic YouTube video about this that I would highly recommend watching. It helps develop this idea, this rigorous idea of what an ellipse is, and that, you know, it's not just an oval. It's a mathematically defined geometric object. Some more information that we should just keep in mind here. So we have what's called the major axis, which is the bigger one. And we also have the minor axis, which is, guess what, the smaller one. We also have a quantity, which we define as being half the major axis, called the semi-major axis, or A. Same thing for the minor axis, but we call it B, and the semi-minor axis. E is the eccentricity. Not Euler's constant. It's the eccentricity in the case of an oval. And this is defined as being 1 minus b squared over a squared. Okay, now on to Kepler's second law. A line joining a planet and a sun sweeps out equal areas during equal intervals of time. Or generalized, the line joining an orbital body and the body it is orbiting sweeps out equal amounts of area over equal amounts of time. What does that mean, though? So let's say we have this model of a star and an orbiting body, right? And we start off here at the red marker, and in time t we go here, so that we have crossed distance d1. And then we move on a little bit, but we keep in mind that time t. In fact, let's call it delta t, this change in time that causes the body to move a distance of d1, okay? And after a while, we end up over here at where A2 is, on the left side of the planet, or of the left side of the star. And we start here, and we move for time t, or delta t, all the way to here, such that we have traversed D2. Now, given that the time taken to traverse D1 and D2 are the same, which we just said they were, the area formed between this point, which, let me put on the red thing, this point, the body that's being orbited, and the beginning point, that area is equal to the same area over here, right? What makes these areas the same is that we have the same setup and we're going traversing the same amount of time. How do we prove this? Well, we'll get into that later. Alright, so Kepler's third law. The ratio of squares of an object's orbital period with the cube of the semi-major axis of its orbit is the same for all objects orbiting the same primary, or simplified. For all objects orbiting the same body, the cube of the semi-major axis is proportional to the square of the orbital period, or a to the 3 is proportional to t squared. We're going to go into a proof of this later. You may have done a proof in your physics class which involved a circular orbit. That one's fairly simple. We're going to go into a more general proof for an ovular or an elliptical orbit. Yeah, that's literally just what I said. Okay, just some quick terminology here. The closest point between the star, or whatever body is being orbited, and the orbiting body is called the periaps. The furthest distance is called the apoaps. Now on to Newton's law of universal gravitation. If you've taken a physics class, you've seen this before. But just to review, F is the gravitational force, G is the gravitational constant, big M is the mass of the object being orbited, M is the mass of the orbiting object, and the square of R is the square of the distance between the two. Okay, now let's tackle centripetal force, or acceleration. Say we have a perfectly circular orbit, for simplicity's sake, and we have our orbiting object, and that orbiting object is moving with speed v1 at the beginning. But then some time passes, and it's orbiting at r, right? And then some time passes, and it's now over here with speed v2, still at distance r. Well, what do we know about these speeds? Well, we know that the speed is the same, but the velocity is different. Why? Because it's pointing in different directions, right? Remember, velocity is speed and magnitude, right? And what has happened here is that the gravitational force is pulling on the orbiting object. Now the gravitational force isn't strong enough to like outright pull it down into the planet, but it is strong enough to kind of reroute the velocity. So they come to like this compromise where it ends up going down a little bit. So look, this wants to go this way, right? Gravity wants it to go down. So they come to a compromise, okay, I'll go here. And they keep making this compromise over and over again, and then you have an orbit. Can we calculate the acceleration caused by gravity based off just the velocity and radius alone? Or more accurately, the speed? Yes. A is equal to v squared over r. Where does this come from? I mean, we've seen it, I've seen it, you've probably seen it. Where does this come from? Well, let's find that out. Okay, so let's take a look at the same setup. We've got v1 and v2, right, as our velocity vectors. Well, let's bring them together and let's say that the difference between these two vectors is delta v, right? And let me make this a bit bigger so that we can see it. So right now, based on this, we can conclude that v1 plus delta v is equal to v2, and that v2 minus delta v is equal to v1, right? And we have the initial vector, or we have the radius vector, r, and we also have the same magnitude, but the different r vector in another direction, with an angle theta separating them. So that's what we have over here. Now, let's say that same theta separates v1 and v2. How do we prove that? Well, the velocity vector is, I don't know if it goes in. Okay, it doesn't say in the slideshow. But the velocity vector is always perpendicular to the radius vector, right? Well, that's one of the it's one of the conditions for tangential velocity anyway. It has to be perpendicular. So if it is perpendicular, right, that means that by whatever angle this changes, that changes too, because they're always just a constant apart. And let's say we draw a straight line between the two radius vectors, right? Well, Let's now make this distance like really, really small. So right now we're not tackling like a big distance, we're only tackling a really, really small distance where the curvature is roughly equivalent to just a straight line, right? So as theta approaches 0, this looks more and more like a triangle, right? And we can call this tiny little difference v times theta t. Why? Because that difference is just going to be this velocity vector, which you can see right here, right, times any change in time. We can use this to create an equivalency. So v times delta t, or v dt if you've taken calculus, where delta t is roughly equal to 0. So really small distance we're talking about here. And again, that's delta v still, remember that. Or dv if you're taking calculus. Again, L, the length of these vectors is equal to v, the v initial, the original speed. So we can use a similarity of triangle statement to say that delta v over the magnitude of the velocity vector is equal to v times delta t over r. And then we can just rewrite this to solve for v over t, which would be equal to v squared over r. And that is our acceleration. Because remember, delta v over delta t is equal to acceleration. Or if you've taken calculus, dv over dt is equal to acceleration. Now, though the examples I showed had a constant centripetal acceleration, the equation still applies in cases where the acceleration is not constant, such as in ellipses. So the centripetal force acting on an object is its centripetal acceleration times its mass, F equals mv squared over r. Now on to Kepler's second law. Let's say that the torque that is done onto the orbiting body is equal to r times f sine theta. Now, so then the net torque is equal to the radius times the sum of all the forces perpendicular to the orbiting body. We also know that the only force acting on this body is going to be the force of gravity from the body that's from the body that's being orbited. What we also know is that the net torque is equal to the change in angular momentum over time. So we can say that dl over dt is equal to r f of g times sine theta. Okay, so the radius vector is there. The force of gravity vector is there, and you'll notice that there is no angle between them. Theta is equal to 0, meaning that there is no perpendicular component, meaning that we set sine to 0 and we discover that dl over dt is 0. That is important because it means that angular momentum is conserved, or that it does not change. No matter what point of the orbit we're talking about, angular momentum stays the same. And that is important and crucial, and we're going to box that and we're going to put it to the side for now. Okay, now let's say that over a tiny period of time, the orbiting body carves out an area of dA. Okay, now let's define dA as a kind of wedge formed by the radius vector and a vector which we're going to call dx. So a change in distance from where the orbiting body was to where it is now. Again, super tiny difference. So small that we can almost treat it as triangular. Even though dx would be curved, we can treat it as triangular at this small of a level, right? Think about like a circle. You get really close to a circle, it becomes what? It becomes flat. Think about our own Earth, right? To us, Earth is so big that the surrounding area looks flat. And to some people it is, but in reality, it isn't. So, if you've taken linear algebra, you may know that the cross product of the radius vector and dx, which I've labeled as a green parallelogram, is equal to, well, the area of the green parallelogram, right? If you didn't take linear algebra, well, now you know. Well, neither have I. So, we know that 1/2 of this green parallelogram, well, that's the wedge which we're looking for. That's dA. So we can write that down and say it like it is. Now, recall that dx over dt, or that the change at tiny area, the dx vector over dt is equal to the velocity vector. So we can say that the velocity vector times dt is equal to dx, and rewrite that into our equation. What now? Well, we can take dt out of the expression because it's a constant. We can take dt out of the expression because it is a constant, right? What that means is that we can move it to the other side and say that dA over dt is equal to 1/2 times the cross product of r and v. What we also know is that linear momentum is equal to m times the vector v. So we can just take an m out, or we can write v as p over m, and we can move the m out because it's a constant. Finally, remember that L, or angular momentum, is the cross product of the radius and the momentum. If you didn't know that, again, that's more of the linear algebra, advanced physics stuff that you don't tackle in a Physics 1 class. But again, now you know. For your purposes, cross product is just going to be one vector cosine. But anyway, that's exactly what we're looking for. So now we know that 1 over 2m times the angular momentum is equal to the change in area over time. Remember that the linear momentum, or remember that the angular momentum stays the same. Remember that the magnitude of the angular momentum does not change. The direction the vector points does, but the magnitude does not, which means that the magnitude of the area drawn out per unit time has to remain constant, right? Because you have a constant on this side, there has to be a constant on that side for it to be equal. And there you go, you're done. That is the proof of Kepler's second law. Not so simple, but pretty elegant. Okay, now let's go and derive Kepler's third law. Let's start with the fact that force, or the gravitational force, is equal to g times mm over r squared. We also know that the centripetal force is equal to mv squared over r. Why are these denoted by the same f? Because if you're thinking about a single body orbiting another one in a perfect circle, those forces are describing the same thing. The gravitational force is the centripetal force. It's the thing holding it in the circle, in the circular orbit. We also know that velocity is equal to angular velocity times the radius, or where the velocity is tangential. We can rewrite the centripetal force equation accordingly. We also know that angular velocity is equal to 2 pi over the period. We can rewrite our centripetal force equation accordingly. Now, let's set the two as equal to each other, which they are, cross out some terms, and we get this. T squared is equal to r to the 3 times 4 pi squared over gm, where 4 pi squared over gm is a constant. Here's the problem though. In an elliptical orbit, the angular velocity changes. Therefore, this statement right here proves not to be true outside of circles, meaning that the proof is only valid in cases of circular orbits, which is unfortunate because it's really easy. Now we're going to go on to the derivation of Kepler's third law. Now when I was making this video, I thought, okay, I'd find a bunch of proofs for everything online, throw them onto a video, do a little narration, and there we are. Well, no, actually, because it turns out there was not a single neat, well-defined source which had a proper proof for Kepler's third law. And you know what? For good reason. Because this is not very fun. Let's start with this red line right here. You want to know what it's called? L, or the semi-lattice rectum. Yes, you heard that right. This is equal to the perpendicular distance between a focus and the curve, or in our case, the star and a point on the orbit, which is perpendicular to the focus. Now, we know from before that the net force is equal to the force of gravity, which is equal to the centripetal force. Plugging in what we know from before, again, we get the gmm over r squared is equal to m times the angular speed squared times r. Recall that angular momentum is equal to rotational inertia times angular speed, or angular velocity. and that in this case, since we're considering the planet to be a point mass, angular momentum is equal to mr squared times omega, which would mean that omega is equal to L over mr squared. Subbing that in, we get this expression right here. Let's do a little bit more rearranging to get this. This gives us a neat little expression for r that we're going to keep. Now let's consider this in the case of the semilattice rectum. So r is equal to L. Let's call in some help from an old friend. Kepler's second law. What does this say? Well, it says 1 over 2m times L is equal to the change in area over change in time. Well, we know that the total area of an ellipse is pi times AB, right? This should have been, you should have gone over this in like a geometry class or something. So we can say that the time it takes for a planet to revolve times dA over dt will equal the total area of the ellipse. So t times dA over dt is equal to pi AB. Now, we can sub in what we know from before to be equal to dA over dt, which is L over 2m, and now we have this expression which we can rewrite as this. I also want you to remember from earlier on in this video actually that the eccentricity, not Euler's constant, is equal to 1 minus b squared over a squared. We can square both sides to get that e squared is equal to 1 minus b squared over a squared, and that b is equal to a times the square root of 1 minus e squared. We can sub that into our equation, and now we have this. Okay, what the hell is this? Well, what happened here is that we squared both sides of the equation that we had before. This is useful. We're going to end up using it. Okay, now on to everyone's worst nightmare, trigonometry. Let's create a triangle that goes from this focus over here, the closest focus to the semilattice rectum, the one which we're calculating it at, to the other focus, right? And let's consider this length, well, the semilattice rectum. Let's consider that one. Let's consider that one to be d, the hypotenuse of this triangle, and the total distance, which is the semi-major axis, as 2a. We know that 2a is equal to d plus L. How do we know this? Well, consider what we knew from all the way back at the beginning of the video when I talked about the basic parameters of an ellipse. The distance between the focus, the two focuses to a point, remains constant throughout the whole ellipse. If you're having trouble visualizing this fact, well, just think about what if it was over here, right? It would be this distance away from this focus, and it would be this distance away from that focus. Add the two distances together, and you have the major axis. So then let's continue. C is equal to, or well, E is equal to C over 2A, right? This means that 2EA is equal to C. We also know that D squared is equal to L squared plus C squared, right? Basic trigonometry. So let's rewrite what we had from earlier. 2a minus L is equal to D. What this means is if we plug that into the Pythagorean theorem expression, we get that 2a minus L squared is equal to L squared plus 2EA squared. A is equal to 1 minus E squared, or A times 1 minus E squared is equal to L. Okay, final stretch. Let's put it all together. L squared over GMM squared is equal to A times 1 minus E squared. We went over this earlier. We also know that T squared is equal to 4 pi squared times A to the 4 times 1 minus E squared M times M over L, right? Putting these two equations together, we get that T squared is equal to A to the 3 times 4 pi squared over GM. Hey, isn't that familiar? Well, that's the same expression we got doing it with the circle in that special case, where 4 pi squared over GM is a constant, and T squared is proportional to A to the 3. Okay, now let's talk about something I don't have. Energy. Right? We have a body that's orbiting right here with a velocity and a kinetic energy of 1/2 mv squared. We have its radius, right, which means that its potential energy is equal to negative mgh, which is equal to negative m times gm over r squared times r, which means that its potential energy is equal to negative g times mm over r. We know that the total energy is equal to k plus u, which means that the total energy of this system, or of the body that's rotating, is equal to 1/2 mv squared plus negative g mm over r. And since no external work is done in a two-body system, this in a stable orbit remains constant. So the energy does not change as long as no other forces outside of the orbit are interacting with it. Why negative though? Where did I pull that from? Well, here's where. Let's consider this to be positive, right? Let's consider this to be negative. So the further we go, the more positive the height becomes, right? Well, if we just like grab it and we take it all the way up there, right? What's going to happen? Well, we've moved it delta x. We've applied a work to it to move it in that direction. And that work can be just expressed as w, or as w is equal to f delta x, right? Well, this potential energy would be g mm over r plus delta x, or the magnitude of this potential energy would be this. This is actually less than the magnitude of our initial potential energy, which means that as we get further away, the potential energy decreases. So if applying positive work causes a reduction in the magnitude of potential energy, the said potential energy must be negative, right? We apply positive work, potential energy goes down, meaning that it must be negative, right? Make sense? Good. Escape velocity. Let's use what we know to calculate something else. The minimum velocity required for an object to escape the gravitational field of another. Right, we have an object and it wants to leave Earth. Well, too bad, but everyone has their own reasons. So we know that right now its potential energy is g mm over r, right? At this point up here, its potential energy is equal to 0, right? Because it's out of Earth's orbit. It's out of Earth's sphere of influence, right? Just as the British had theirs, Earth has its own, right? So what it wants is to be outside of this sphere of influence, right? What is the minimum velocity for it to do so? Well, by logic, it has to have a velocity of 0 whenever it reaches this point, right? It has to use all of its energy to get up there and have nothing left in the tank. That means that the energy final is equal to 1/2 m times 0 squared plus 0, right? Or that energy final is equal to 0. Energy initial is equal to energy final. What this means is that energy initial also has to be equal to 0. Therefore, 1/2 mv squared plus negative g mm over r has to be equal to 0. You set the two as equal to each other, solve for v, and you get this expression right here. Vi is equal to 2gm over r. Now onto the v-viva equation. Not the viva la vida equation, it's the v-vita equation, which states that the velocity of an orbiting object is equal to the gravitational constant times the mass of the object being orbited times 2 over r minus 1 over a, where a is our good friend, the semi-major axis. Okay, so let's define this quantity called specific energy, which is the energy of an object divided by its mass. So since we know the energy of an object in an orbit is this, we can say that its specific energy is this, where we just divide everything by m, right? Now, let's say its energy at the periaps is equal to 1/2 v at the periaps squared minus gm over r at the periaps. Its energy at the apoaps is the same thing, but instead of Vp, we're looking at Va. We know that since the total mechanical energy is conserved, the mass is the same, that the Ea is equal to Ep. There, or it's epsilon, but I'm going to say E because it's easier, which means that this equation here holds. Ea is equal to Ep. We just sub these in, we move some stuff around, and again, that's the apoaps, that's the periaps. Again, we have this expression. Remember that angular momentum is conserved, which means that the angular momentum at the apoaps is equal to the angular momentum at the periaps, which means that mva times ra, because we're considering the planet as a point mass, is equal to mvp times rp. which means that VA times RA is equal to VP times RP, which means that VP is equal to VA times RA times over RP, which we can sub into our expression over here. From here, we can just clean it up a little bit, and now we have this. Again, remember that's the apoapse, the periapse. The periapse plus the apoapse is equal to the semi-major axis, or 2a, which means that RA plus RP is equal to 2a. We can use that and sub that into our expression. And we also know that RP is equal to 2a minus RA. We can sub that into our expression. And so we get this. Do a little bit more simplification. Remember that EA is equal to 1/2 times VA squared minus GM over RA. So epsilon is equal to GM over RA minus GM over 2A minus GM over RA, meaning that epsilon is equal to GM over 2A. Since this is conserved, we can set this as equal to our expression earlier, rewrite some stuff, and there you have it, the V-Viva equation. My work here is done.